Okay, let's dive into this. Welcome to The Explainer. Today, we're unpacking a literal intellectual masterpiece, a book that completely shatters the illusion of absolute scientific certainty. We're exploring Henri Poincaré's Science and Hypothesis. Published over a century ago, this text fundamentally challenged how we understand the scale of reality, the rules of math, and honestly, the very fabric of the physical universe.
So, I want to start by posing a pretty provocative question here. Is the logic of science infallible? As laymen, we tend to look at science as just this giant, unassailable pile of rigid facts. We think, hey, if an experiment says something, it's an absolute objective truth handed down by the cosmos, right? But Poincaré forces us to really look in the mirror and ask if the tools we use to understand the universe, our math, our geometry, our physical laws, are actually realities or just incredibly useful human inventions.
Just look at this fantastic quote from the book. Poincaré writes, "A breath would bring them to the ground. Hypothesis is as necessary to the experimenter as it is to the mathematician." I mean, wow. He realized that without hypothesis, without human convention, and frankly, educated guesswork, the entire structure of science would literally just collapse. Facts alone aren't enough. Hypothesis and human convention, those are the true beating engines of scientific discovery.
Let's move through the agenda and see how this all builds. First, we'll cover the nature of mathematical truth, then inventing the mathematical continuum, geometry as convenient convention, mechanics and disguised definitions, the power of hypotheses, and finally, navigating ignorance with probability.
Section 1. The nature of mathematical truth, beyond simple tautologies. So think about it. If math is just a series of logical deductions, isn't it kind of just a massive tautology? Isn't it just an endless, super complicated way of saying that A equals A? Well, the answer to how math actually creates new truths lies in proof by recurrence. Here's how it works. You verify a theorem is true for the number 1. Then you prove that if it's true for the preceding number, it must be true for the current one. From this, the mind just concludes it's true for all integers. This isn't just regurgitating facts. It's an active assertion of the mind's power. It allows our finite human brains to creatively leap over an infinite number of verifications. Mathematics isn't just a giant tautology. It's a testament to the mind's incredible ability to grasp infinity.
Section 2. Inventing the mathematical continuum. Fixing the flaws of human perception.
Now that we understand how the mind generates mathematical truth, we've got to look at how we apply it to a physical world we only experience through our deeply flawed senses. Take the physical continuum, for example. If you hold a 10-gram weight, it feels completely identical to an 11-gram weight, so A equals B. And an 11-gram weight feels identical to a 12-gram weight, so B equals C. But if you compare the 10-gram and 12-gram weights side by side, you can actually feel the difference. Suddenly, A is less than C. This is an intolerable, totally illogical contradiction. And this brilliantly illustrates our point. To fix this glaring error in our physical perception, the human mind essentially invented the mathematical continuum, an infinite, perfectly divisible scale. We created it literally to iron out the chaotic, contradictory data our own senses feed us. Section 3. Geometry as convenient convention, the framework we impose on the world. Okay, so if our math is an invention to fix our senses, what about space? We've all been taught to think that the three-dimensional rules of space and geometry are absolute truths, right? Handed down to us by the universe itself. But Poincaré delivers a massive aha moment here. He writes, "Experiment tells us not what is the truest, but what is the most convenient geometry." When non-Euclidean geometries were discovered, geometries where parallel lines can intersect or the angles of a triangle don't actually add up to 180 degrees, it proved that our standard everyday geometry isn't the only truth. It's simply a chosen language. We use three-dimensional Euclidean geometry because it's best adapted to our bodies and our physical impressions. It's not some absolute truth of the universe. It's just the framework we find most convenient to impose upon it.
Section 4. Mechanics and disguised definitions. The laws of classical physics.
Now, let's shift gears from the geometry of space to the forces that actually move through it. Think about Newton's incredibly famous law, force equals mass times acceleration, or F equals ma. We're taught this as a fundamental law of nature. But now, what's really interesting about this is that Poincaré reveals this is not actually an experimental truth. We don't have a way to measure force completely independent of mass and acceleration. Therefore, F equals ma is essentially just a definition we created. We built the definition because it works beautifully, for sure, but we always have to remember that it is a human-made convention.
This right here is one of the ultimate reveals of Poincaré's work.
Look at the original observations versus their final scientific status. A concept like inertia starts as an experimental truth, like a ball rolling on a table. But concepts like force, or the idea that every action has an equal and opposite reaction, we can't perfectly isolate systems in the universe to prove these absolutely. So, what do? We elevate them. We take an imperfect experimental observation and declare it an absolute principle. They become definitions in disguise, agreed-upon rules that we pledge never to contradict simply because they are just too convenient for doing science.
Section 5. The power of hypothesis. Generalizing the observable universe.
So, if our math is a mental creation, our geometry a convenience, and our physics full of disguised definitions, how does a physicist actually get any real work done? Poincaré uses a very concrete, honestly almost funny analogy. Imagine someone tells you, King John Lackland passed by here. Okay, that's a fact. But as an isolated fact, it's completely useless for science, because, well, he's never going to pass by here again. Merely cataloging detached facts is not science. To be useful, science requires generalization. We have to take a fact, assume it points to a wider law, and use it to predict the future. And that generalization inherently requires making a hypothesis.
But we have to be careful, because not all hypotheses are created equal. Poincaré breaks them down into 3 types. First, natural or necessary hypotheses. These are the basic assumptions we literally can't do without, like assuming very distant stars have a negligible effect on our pendulum experiments. Second, indifferent hypotheses. These are harmless metaphors. For a long time, whether you viewed matter as completely continuous or made up of individual atoms, the math worked out exactly the same. It was a useful image, but didn't change the immediate results. And finally, real generalizations. These are the testable laws. These are the risky, exciting engines of discovery that absolutely must be rigorously verified or brutally abandoned by experiment.
Section 6. Navigating ignorance with probability. The calculus of the unknown.
All right, here is the humbling reality of science. We can never know all the facts. We can never perfectly measure every starting condition of a complex system. So, how do we categorize what we don't know? Well, Poincaré outlines 3 degrees of ignorance. In the first degree, we know the natural law and the initial state. That's just simple math. In the third degree, we know neither the law nor the initial state, which means we know absolutely nothing. But look at the second degree. We know the laws of the system, but we do not know the initial state. So the crucial point is, this is where physicists actually operate most of the time. And it is right here that the calculus of probabilities becomes our guiding light.
To see this in action, let's look at predicting the current distribution of minor planets in our solar system. If we want to predict their current distribution, we have a known factor. We know they obey Kepler's laws of motion. But we also have a massive unknown factor. We have absolutely no idea what their initial distribution was millions of years ago. By applying the calculus of probabilities, we can bridge this gap. We just assume a continuous uniform distribution over time, which allows us to predict their current state even when our knowledge is fundamentally incomplete. Probability basically turns our ignorance into a workable model.
And that brings us to the climax of Poincaré's philosophy. Nature, playing with analytical difficulties, only uses simple means. We must stop where we have found simplicity. If we drill down far enough, every single phenomenon is unimaginably complex. A gas in a jar is literally billions of molecules colliding completely unpredictably. But at a macro level, it obeys a simple law of pressure and volume. We have an instinct of simplicity. To make any progress at all, we must intentionally stop our analysis at a level where we find a workable, simple model.
Let's summarize this entire journey by contrasting where we started with where we are now. The layman's view assumes science is a pile of absolute, rigid, complete facts dictated by the universe. But Poincaré's reality reveals something so much more profound. Science is a beautiful, collaborative dance. It's an ongoing negotiation between human convention, the frameworks of our mathematical minds, and the humbling reality of experimental observation.
Which leaves us with this final, truly provocative thought to take away today. Are the laws of nature genuinely written by the universe, or are they simply the most convenient stories invented by the human mind to make sense of the chaos? It challenges literally everything we think we know about reality, and I really hope it leaves you just as hungry to explore further as it does me. Thank you so much for joining me for this explainer.